Central limit theorem. Objectives: to discuss and explain why do we need to analyze the central limit theorem, to apply it in real life of central limit theorem. Always use the C-table values and scientific calculator. So this photo represents as the standard normal distribution of the table value, using the left at the C-score. This is the negative. And the other one, the C-table values for the positive. What is central limit theorem? It is stated that if you have a population with a mean, or the probability mean, and the standard deviation of sigma, and take sufficiently large random sample from the population with replacement, then the distribution of the sample means will be approximately normally distributed. This will hold true regardless of whether the source of population is normal or it's skewed. Then it provides a sample size is sufficiently large. That is usually the number of samples as n greater than or equal to 30. Central limit theorem. If the population is normal, then the theorem holds true, even for samples smaller than 30. In fact, this also holds true even the population is binomial, provided that the mean, or the NP, stands for n multiplied by 1 minus p greater or equal to 5, where n is the sample size, and the p is the probability of the success in the population. This means that we can use the normal probability model to quantify uncertainty when making inferences about the population mean based on the sample mean.
Here I come from the west side, the left side, the right brain
So this is the formula,
drives me in.
where z is the z-score and x is the average mean, and then mu is the probability mean, sigma is the standard deviation, and n is the sample size, n is greater than or equal to 30. So the formula will be z is equals to the average mean minus the probability mean divided by the standard deviation divided by the square root of n. Central limit theorem and approximating the normal distribution.
More carrots.
To recap, the central limit theorem links the following two distributions:
Where's Garrett?
the distribution of the variable in the population, the sampling distribution of the mean. Especially, the central limit theorem states that regardless of the variable's distribution in the population,
The right brain.
the sample distribution of the mean will tend to approximate to the normal distribution.
Same. Don't lie, don't lie, don't lie to me. Don't fry, don't fry, don't fry.
General idea for central limit theorem.
Brain.
Regardless of the population distribution model, as the sample size increases, the sample mean tends to be normally distributed around the population mean. and its standard deviation shrink as n increases. So I will represent a photo. Look at this one. Graphically, the picture below shows one of the simplest type of test, toss of a coin. The more you likely the shape of the distribution of the means tends to look like a normal distribution graph. Okay, suppose you have a one coin, it is normally distributed, so it means to say it has an equal on this histogram. If only one coin, take note. So it is already a straight line from this one, and the histogram is always equal if it's only one coin. While if you have a two coin or toes, so this will be the first, this will be the second, and this will be the third. But normally, if you will look the graph, it is likely have a 10 to be normal. I repeat, it is likely to have a 10 to be normal. And if you have n, which is the 5 coins, toes of a coin, then therefore, this will be represented as the histogram. So, it is likely 10 to be a normal. If number of coins is 10 coins, take note, 10 coins is being toes, it is likely to be normal from the histogram. So, and if n is 50, so going to steep up to n is to 100. That's the reason why in central limit theorem, the more n as the number of sample size, it means to say the shape of the distribution of means gets steeper and steeper from the normal distribution graph. Theorem of central limit theorem. Suppose let have an x of 1, x of 2, up to x of n. So it depends only. Huh? Take note. If you have x of 1 as 1, x of 2 as 2, and then x of n is 30. Suppose be a random sample from a distribution. What is random sample? You will choose any number from 1 to 30, then 7, 8, 9, or 10. So with the mean or the probability mean and variance. So if n is large enough, as approximately a normal distribution with the variance and variance divided by the number of n. With a large enough, it depends in the class, we'll say that n is 30 is large enough. Some certain condition must be met to use the central limit theorem. The sample must be independent. The sample size must be big enough. Central limit condition. First, independent sample test. We need randomization. Each sample should represent a random sample from the population, or at least follow the population distribution. 10% rule. The sample size must not be bigger than 10% of the entire population. Large enough sample size. The sample size or n should be large enough so that n is greater than or equal to 30. Central limit theorem as a sample. Suppose you have an x of 1, x of 2, and x of n. For example, x of 1 is 1, x of 2 is 2, up to x of n is 30. So 1 plus 2 plus 3 plus 4 plus up to 30. are n as the random variables that are independent and identically distributed with the mean, for the probability mean and the standard deviation. Suppose you will get also the sample mean. So x is equals to x plus 1, x plus 2, plus x of 3 up to x of 30 divided by n as 30. You will get the sample mean or the average mean. We can show that the average mean is equal to the probability mean, and then the standard deviation mean is equals to the standard deviation divided by square root of n. The importance of central limit theorem. As the sample size increases, the distribution of frequency approximates as a bell-shaped curve. Example that is the normal distribution curve. Sample size equal or greater than 30 are required for the central limit theorem to hold true. A sufficiently large sample can predict the parameters of population, such as the mean and the standard deviation. So this will be the theorem. With the random samples, we can take the population, we can compute the mean of the sample mean. So, mean or the average mean is equals to the probability of mean. Standard error or standard deviation of the sample means. Theorem. Standard deviation mean is equals to the standard deviation divided by the square root of sample size. So this will be the formula. Standard deviation mean is equals to the standard deviation divided by the square root of n. Problem number 1. You draw a random sample of size n is 64 from a population with a mean of 50 with a standard deviation of 16. From this, you can compute the sample mean. A. What are the expectation and the standard deviation of the mean? First, we know that the average mean is equals to the mean, which is the 50. This will be the first step. And then followed by the standard deviation or the standard error, or the standard mean or standard deviation mean is equals to the standard divided by square root. So, our standard deviation is 16. Our number of n is 64. So, we have the answer of the standard error or the standard deviation of the mean is 2. So look at the sample. The sample mean has expectation of 50 and the standard deviation of 2. By the central limit theorem, the sample mean is approximately normally distributed. By the use of the empirical rule, there is roughly 2.5% chance of being 54. So the two standard deviation above the mean. So if we will graph in the empirical rule by the mean, we have 50, 52, and 54. So the next will be 56. So this will be the explanation for number 1. So it is normally distributed. Problem number 2. You draw a random sample size n is 16 from a population with a mean of 100 and the standard deviation of 20. From this, you compute the sample mean. Find the standard deviation. First step, that the average mean is equals to the probability mean, which is the 100. And therefore, we can compute the standard deviation mean is equals to the standard divided by square root of n. So our standard deviation is 20. and then the number of n is 16. So 20 divided by 4 is equals to 5. So the probability, the sample mean, is between 295 and 105. The sample mean has expectation of 100 and the standard deviation is 5. If it is approximately normal, we can use the empirical rule to say that 68% of being 95 and 100 with one standard deviation of its expectation. So this will be the graph. If the mean is 100, you will add 5. This will become 105. And then 100 minus 5 will become the 95. So we know that this area from positive 1 to the negative 1 is approximately 68%. And that is normal distribution. Problem number 3. Suppose the grade 5 disciplining mathematics class are normally distributed with a mean of 75 and the standard deviation of 5. What is the probability that a random selected student had a grade at least 83? Letter B. What is the probability that the average grade for 5 randomly selected students was at least 83? So this will be the explanation of problem number 3. We know that this will be the distribution of the average and the standard deviation of 75.5. So the average mean is 83 minus the probability mean divided by the standard deviation of 5. So 83 minus 75 divided by 5 is 1.60. We know that the 83 in the x greater than equal to 83 is a probability z distribution of 1.60. And then 1 minus, so going to the right, take note above or equal, 1 minus 9.552 is equals to 0.0548. So if you will graph this one, this is the mean. 75 plus 5 will be 80, and then 80 will be the 85, 85 plus 5 will be the 90. This belongs to, take note, this will be 1.6. So, how do we get the 1.6? C is greater than 1.6. 1 minus the value of the given, and the answer is around 0.0548. Okay, problem number 3. What is the probability that the average of grade 5 randomly selected student was at least 83? So, normally distributed as the average mean is 75 and our end distribution is 5 divided by the randomly selected as 5. So, we will use the 83 minus 75 divided by 5 and then the square root of 5, which is the n, randomly selected. So 83 minus 75 and 5 divided by the square root of 5, the answer is 3.57. So P is the average mean greater than equal to 83, and then C is greater than equal to 3.57. How do we get the value of 3.57? We will get 1 and the table value of 0.99. Take note, the value of 3.57 in the table value is 0.99 and the answer is 0.001. Is this appropriate? The answer is the problem is not appropriate to answer the problem number 2 because Z is 3.57. It is above 98. And n should be greater than equal to 30. So if this is 75, this will be the 80 and somewhere is the 83. 85 to 95. So the problem is not approximate to answer the problem number. Problem number 4. If it happens that the age of cars on the road is normally distributed with a mean of 7.2, if the standard deviation is to be 2.1 years, what is the probability of 12 randomly selected cars have been on the road for between 6 to 8 years? This was solution for problem number 2. Take note, the average mean and the normal distribution. The average mean is 7.2 and the standard deviation is 2.1. With randomly selected a square root of n of 12. First, we need to have a formula for the z-score, which is the 6. We will start from the 6 minus 7.2 divided by 2.1 and then divided by square root of 12. The answer is 1.98, so negative 1.98. While the z2, which is the 8 minus 7.2 divided by 2.1 as the standard deviation and the random size of square root of 12, the answer is 1.28. So our probability will be 6 less than or equal to the average mean less than or equal to 8. So the value of negative 1.8, take note, the value of negative 1.8 is 0.9066, while the 1.32 is 0.239. How do we graph this one? Do you think it is correct? So the first step that you will do is to draw the x and y axis and then the normal curve. So the average mean, take note, the average mean is 7.2. You will replace it here, 7.2. And the standard deviation is 2.1. 7.2 plus 2.1 will be 9.3. 7.2 minus 2.1 will be 5.1. And then, we are looking for the 6 years and 8 years. According to the Z1, the value is negative 1.98. Take note of 1.98. And the other one of 8, for the C2, the value of C-score is 1.3. Do you think it is approximately wrong? This is very wrong because 5.1 and 9.1, so maybe around here the 8 and the other one is 6. Problem number 4. In recent study reported September 29, 2012 on the drug block, the mean of the tablet user is 34 years. Suppose the standard deviation is 15 years. Take a sample size of n is equal to 100. So first, what are the mean and the standard deviation for the sample mean ages of tablet users? What does the top distribution look like? Find the probability that the sample mean age is more than 30 years. The reported mean of age of tablet users in this particular study. Find the 95% for the sample mean of age to 1 decimal places. This will be solution explanation of problem number 1. So therefore, number 1, since the sample means tends to target the population mean, first we have the average mean is equal to the probability mean, which is 34. Take note that the average mean and the probability mean is equal to 34. So how do we get the sample standard deviation? So the given will be the standard deviation is 15 and the number of sample size is the square root of 100. So what will be the square root of 100 is 10. So 15 divided by 10 is 1.5. Take note, number 2, the central limit theorem states that the large sample size of n, the sampling distribution will be approximately normal because large sample size n is greater than equal to 30 because our n is 100. The probability that the sample mean age is more than 30 is given by x, or probability x greater than 30. And if you will look in the normal distribution, so we will have around as 99 or 34.15, around 0.9962. So it's under part the 95 percentile rank for the K, or the 0.95, the 34, 15 divided by square root of 100, and then the answer is 36.5.